All right, so we're back for another deep dive, and today we're tackling a problem that even stumped the great Isaac Newton,
Oh, this is gonna good.
the three-body problem. Yeah, and the Star Talk video with Neil deGrasse Tyson will use that as a guide to kind of explore this whole idea of orbital mechanics and chaos.
Sounds like a plan.
Okay, so starting with the basics, Truth. Everyone knows that the Earth orbits the sun, but what's really happening is
It's not just the Earth going around a stationary sun, right?
exactly, they're actually both orbiting a common center of gravity.
And because the sun is so much bigger than the Earth, that center of gravity is like,
Inside the sun.
you got it. It's inside the sun, but it's not right at the sun's center.
So it's almost like a cosmic dance around this invisible point within the sun.
You could say that. And as the Earth moves along in its orbit, that center of mass shifts a little.
Oh, so the sun kind of wobbles in response.
Exactly. That's the two-body problem, and thanks to Newton, we've got that figured out.
But what happens when you add another object into the mix? Like Jupiter.
Ugh. Now we're getting to the heart of it. That's the three-body problem.
And I'm guessing that's where things get a bit more complicated.
You could say that. The two-body problem is elegant, straightforward, but with three bodies and their gravity, things get messy.
So even Newton couldn't crack this one.
Well, he struggled with it, especially with how Jupiter might affect the Earth's orbit.
I mean, Jupiter IS, the biggest planet in our solar system, right?
Yeah, and Newton worried that Jupiter's pull might mess things up.
Destabilize the whole solar system.
Exactly. He was afraid the planets might just go spiraling off into chaos.
Yikes. So did he ever figure out a solution?
Well, not exactly. He kind of came up with an interesting explanation. He thought that God stepped in every now and then to keep everything in order.
Wait a minute, so even Isaac Newton resorted to divine intervention.
It sounds strange now, but back then that was a common idea. It was a way to reconcile the stability we see with the physics they understood.
So what happened next? Did anyone challenge that theory?
Oh, yeah. About 100 years later, a French mathematician named Pierre-Simon Laplace took on the three-body problem.
What did he come up with?
He developed something called perturbation theory.
Perturbation theory. What's that all about?
Okay, imagine dropping a pebble into a pond. See those ripples? Those are perturbations caused by the pebble.
So in space, those ripples would be the gravitational effects of the planets on each other.
Exactly. Perturbation theory lets us calculate those tiny ripples or perturbations even if they're very small.
So instead of thinking of Jupiter's gravity as this huge force messing everything up, Laplace found a way to study its smaller effects over time.
Precisely. He showed that those little gravitational nudges could actually lead to a stable system in the long run.
Because they sort of balance each other out.
You got it. And that meant no need for divine intervention.
No need for God to keep things running smoothly.
Exactly. There's a famous story about Laplace and Napoleon. Napoleon asked him why God wasn't in his work, and Laplace said,
I bet he had a pretty good comeback.
He did. He said, I had no need for that hypothesis. Mic drop.
Wow. That's pretty bold. It sounds like this was a major shift in scientific thought.
It was. It really highlighted the power of math and observation to explain what we see in the universe.
Showing that even systems that seem chaotic might have an underlying order.
Exactly. And it really shifted the focus away from divine intervention and towards the idea that we can understand the universe through science.
This is fascinating stuff. But while Laplace seemed to solve the question of our solar system stability, what about other three-body systems? Like that famous binary star system in Star Wars, with a Tatooine orbiting two suns.
Ah, great example. That's what's called the restricted three-body problem.
Restricted, so it's a simplified version.
In a way, yeah. In this case, you have two big objects, the stars, and then a much smaller object, Tatooine.
So the planet's gravity is so small, it doesn't really affect the star.
Exactly. And in the Star Wars example, Tatooine is far away from the two suns, so the sun's gravity kind of acts as a single force on the planet.
Like they're working together to keep Tatooine in a stable orbit.
That's the idea. That's how a planet can exist in a binary star system.
Okay, so we've got the two-body problem down, and we see how a specific three-body problem can work. But what about the classic one? With three objects of similar mass, is there any hope for stability there?
Now that's where things get really interesting and kind of messy. Imagine juggling three fists at once.
Oh, that sounds chaotic.
It is. And that's because three bodies with comparable mass create a system that's inherently chaotic.
So unlike the two-body problem or the restricted three-body problem, there's no neat solution.
No simple, predictable answer.
So chaos reigns supreme. What does that actually mean in a mathematical sense?
In math, chaos means the system is incredibly sensitive to its starting conditions. Even a tiny change in where those objects are or how fast they're moving can lead to completely different outcomes.
It's the butterfly effect, but on a cosmic scale.
Exactly. And it's not just that the outcomes are different, they diverge exponentially over time.
So the longer the system goes on, the more unpredictable it gets.
You got it. Even with our best math and computers, we can't predict the long-term behavior of a true three-body system.
Wow. So it's not a limitation of our technology. It's like a fundamental limit to what we can know.
Exactly. It's a property of chaotic systems. There's just a limit to how much we can know about the future.
Mind-blowing.
Mm.
So does this mean that star clusters with hundreds or thousands of stars are just complete unpredictable messes?
Well, it's true that trying to predict the exact position of each star over a long time is nearly impossible.
So what do scientists do? Just give up?
Not at all. Instead of tracking each individual star, scientists use statistical models.
So they're looking for the bigger picture, not the individual movements of each star.
Precisely. They focus on the overall distribution of stars, their velocities, and how the cluster evolves over time.
It's like accepting the chaos, but still finding ways to understand it at a larger scale.
Exactly. And you know what? These statistical models have actually taught us a lot about star clusters and how they interact with galaxies.
It's amazing how we can find order and insight in what seems like chaos.
It really is.
So to recap, we started with the elegant two-body problem, moved on to the restricted three-body problem, where a small object orbits two larger ones, and we ended up with the mind-boggling chaos of the classic three-body problem.
It's been quite a journey through history and physics.
Definitely. And it shows how this problem has challenged some of the greatest minds, from Newton to Laplace.
It's a testament to human ingenuity that we've been able to understand even a little bit about these complex systems.
But it also shows that there's so much more to learn about the universe.
Absolutely. And the three-body problem reminds us that the journey of scientific inquiry is ongoing.
Well said. Now, before we finish this part of our deep dive, I want to leave you with something to think about. We've seen how the three-body problem highlights the limits of classical physics in predicting the behavior of chaotic systems. So how do you think this idea of chaos in seemingly predictable systems might apply to things like AI or economics?
That's a really interesting question.
It's something to ponder as we continue exploring the three-body problem.
Yeah, it really makes you think, is anything truly predictable when chaos is a part of the universe?
It's true. We started with a simple question about orbits, and now we're down this rabbit hole of complexity.
That's the beauty of the three-body problem. It's not just a theoretical puzzle. It has real implications for how we understand space.
Speaking of space, how has this understanding of the three-body problem changed how we approach things like space exploration?
It's been huge. Think about sending a probe to another planet. You have to factor in the gravity of the sun, the planet itself, and any other celestial bodies nearby.
Oh, wow. It's like cosmic billiards. You need the perfect shot to reach your destination.
Exactly. And it's not just within our solar system. Understanding the three-body problem is crucial when we study binary star systems.
Which are pretty common, right?
Oh, yeah. And even though we can't perfectly predict the movements of three stars, we can still learn a lot about them.
The things like their masses, their distance from each other, and how they change over time.
You got it. And that information helps us understand galaxies as a whole.
So even in the face of chaos, there's still order to be found.
There is. And this understanding of chaos has even influenced other fields of science. The principles we talked about, like sensitivity to initial conditions and the limits of predictability, apply to a lot of complex systems.
Like what? Give me some examples.
Well, take weather forecasting. Even with all our fancy models, predicting the weather accurately over long periods is hard.
Because of the chaotic nature of the atmosphere.
Exactly. A tiny change in temperature or wind can lead to totally different weather.
The butterfly effect in action.
That's it. And it's not just weather. The stock market is another chaotic system.
Oh, yeah. There are so many factors influencing it.
Yeah.
Economic indicators, what investors are feeling. It's no wonder it's so hard to predict.
Exactly. So we have to recognize that even with our best efforts, there will always be some uncertainty.
So are you saying we should just give up trying to predict the future?
No, not at all. It's about understanding the limitations of our models and finding new ways to deal with complexity.
So instead of looking for perfect predictions, we need to focus on broader patterns and probabilities.
Precisely. The universe is a dynamic and ever-changing place, just like the three-body problem.
It certainly keeps things interesting.
It does. It's part of what makes studying the universe so captivating.
All right, so to sum up, we've seen how the three-body problem has changed how we view the universe. From Newton's divine intervention to Laplace's perturbation theory.
We've explored the chaos inherent in these systems and how understanding it has impacted fields beyond astronomy.
And we've learned that the three-body problem is a reminder of the limits of predictability and the importance of accepting uncertainty.
It's been quite a journey from the predictable two-body problem to the mind-boggling complexity of three bodies.
It has. But there's one last thought I want to leave you with.
Okay, I'm listening.
We've been focusing on the scientific side of things, but what about the philosophical implications? Laplace rejecting divine intervention was a big deal back then. How did that shape scientific thinking? And what does it mean for us if even something as basic as gravity with three bodies can be so unpredictable? Makes you wonder if we can ever really know everything about the universe.
Right. It's humbling. For centuries, people thought that with enough knowledge, the right equations, we could predict everything. But the three-body problem throws a wrench in that idea.
It really does. Like the universe is saying, nope, not so fast. I've still got some tricks up my sleeve.
Exactly. Even with something as fundamental as gravity, it reminds us that there are still mysteries out there and that we need to be open to complexity.
It's almost like a reminder that the universe isn't just some giant clock, and it's not all predictable. There's randomness, there's creativity. That's what makes it so interesting.
I like that way of putting it. It highlights the beauty of the cosmos. It's not just about finding the answers, it's about exploring and realizing that the universe is always changing, just like our understanding of it.
So well said. Going back to that Star Talk video, what was the most interesting thing about Neil deGrasse Tyson's explanation of the three-body problem?
What really struck me was how he emphasized how this problem, which seemed like a failure for classical physics, actually opened up a whole new way of thinking. Scientists had to confront the limitations of their models and really embrace the idea of chaos.
Right. It shows that scientific progress isn't always a straight line. Sometimes the biggest discoveries come from unexpected challenges, from realizing that we don't know everything.
Absolutely. And those moments of, wait a minute, we don't know that, often lead to the most exciting breakthroughs.
So as we wrap up our deep dive into the three-body problem, what's the one thing you want our listener to take away from all of this?
I'd say the next time you look up at the night sky and see all those stars and planets, remember that what seems like a peaceful dance is actually way more complex than we think. There's a whole hidden world of gravity and chaotic movements. And that's okay. It's that complexity, that unpredictability that makes the universe so fascinating.
That's a beautiful way to put it. It reminds us that there's still so much to discover, and that the universe always has more surprises in store for us. So keep asking those questions, keep exploring, and never lose that sense of wonder about the cosmos.
That's what it's all about.
Until next time, keep looking up.